Welcome back to this video series on the topic of expansion and empowerment. Chapter D, the binomial expansion. In this lesson, you'll learn how to expand higher order brackets using something called the binomial theorem expansion technique. Before that, let's have a look at a famous pattern called Pascal's triangle. Pascal's triangle is a pattern that may be used to predict the coefficients of the binomial expansion. The numbers within the pattern may be calculated by summing the numbers immediately above the cell of interest. Now, if we look below, we've got a little bit of a template happening, and I'm going to start this template off by putting the number 1 at the very top. Now, what we're going to do is we're going to generate Pascal's triangle from this pattern shown over here. Now, the way in which this works is the numbers within the pattern may be calculated by summing the numbers immediately above the cell of interest. So if you've got the cell of interest here, the way in which you predict the numbers inside it are you sum the numbers that are above it. So in this case, the only number above is 1, so it's 1. And of course to the right, the only number above this cell here is 1, so it's 1. Okay, moving down. It's not that much more interesting. If we look on the far left, the only number above it is 1, and on the far right, the only number above is 1 as well. However, where we change the pattern up a little bit is in this middle cell. You'll see that there are 2 cells above, so there's a 1 and a 1, and the number that goes in here is the sum of these 2 cells, so 1 plus 1 is 2. So instantly we see the first pattern emerging. Next, the 2 outer cells are 1 and 1 respectively, because they're the only numbers immediately above. But in the middle we have a 1 plus 2, so that's 3. And then 2 plus 1 is 3. Finishing this off, we have 1 and 1. On the far left we have 1 and a 3, which is a 4. 3 and 1, which is 4. And then 3 and 3 becomes 6. So what we have here is a pattern called Pascal's triangle. Now this is useful because Pascal's triangle can be used to predict the coefficients of the binomial expansion. Now that might seem like a lot of words for now, but consider if we have something of the likes of x plus, let's go a plus b all squared. We know that this is going to expand out to be a squared plus 2ab plus b squared. And why this is useful is because this 2 over here is represented by this 2 within the triangle over here. So this is a second order expansion. Second order because we've got the 2 here. Now if that's second order, then the next row down would be third order. And then fourth order, and so on. So what you might be able to predict by now is that while we can expand stuff like a plus b all squared, using Pascal's triangle we're able to expand stuff like a plus b to the power of 3, a plus b to the power of 4, a plus b to the power of 12 if we wanted to do that, and we're able to do that by using the coefficients generated within this pattern over here. Alright, let's have a look at how we can actually put this to use. What we're going to do is we're going to expand 3 examples. So in example 1a we have expand the following using the binomial expansion, so x plus 1 to the power of 4. Now you might instantly think, well yeah, I can expand that, I'll just go x plus 1 all squared, x plus 1 all squared, and then you might expand that out using the perfect square and then using the FOIL method, but that's not efficient in this case. Rather, what we're going to do is we're going to employ a little bit of a pattern here. Now just bear with me. The way in which this is going to be done is firstly we're going to start off by just doing the powers. So first power is going to be a is x, so we'll say that's x to the power of 4 multiplied by b, which is 1, to the power of 0. Then I'll put a plus and I'm going to leave a bit of a gap. Next, I go x to the power of 3 1 to the power of 1, plus, leave a gap, x to the power of 2, 1 to the power of 2, plus, x all to the power of 1, and then the b, which is 1, all to the power of 3, and final gap, x to the power of 0, and then 1 to the power of 4. Okay, this is the first part of the expansion done. Next, I need to go get the coefficients. Because this is a 4th order, what we need to do is we need to grab the numbers in the 4th order column or 4th order row of Pascal's triangle. So 1, 4, 6, 4, 1. Putting these down, I'm going to go 1, 4, 6, 4, and 1. Okay, so this is the expansion basically complete now. All we need to do is actually multiply out the numbers that we have here. So in this case, I'll first deal with the powers. So the 1s can go because they're implied, and this will be x to the 4, and then 1 to the 0 is simply 1, so that will stay like that. Next, we have 4x to the 3, and 1 to the 1 is just 1, plus 6x to the 2, and then 1 squared is just 1, plus 4x to the 1, but I don't need to show that, so I just leave it as 4x, and 1 to the 3 is just 1. And then I can leave out the 1, and x to the 0 is simply 1 multiplied by the 1. Okay, finishing this off, x to the 4 plus 4x cubed plus 6x squared plus 4x plus 1. And thus we're able to show how we can expand rather high-powered brackets elegantly and efficiently using the binomial expansion, where we get our coefficients from Pascal's triangle. Alright, let's have a look at another example that's an even higher power. We've got x take 3 all to the power of 5. What we're going to do is we're going to expand this again in 1, 2, 3 steps using the pattern that we employed up here and the coefficients that we can gather from Pascal's triangle. So we've got x takes 3 all to the 5. I'm going to use the pattern again. So it's going to be a is x, so that's x to the 5, then minus 3 to the 0. Put in my plus, and I'll run the pattern again. Okay, so I've started it out. Now I need to go collect my coefficients. So this is to the power of 5. So what I need to do is I need to go to the 5th order column. Now this one's not generated, so I'll quickly generate it. This will be 1, this will be 5, this will be 10, 10, 5, and 1. So I simply sum the numbers above to figure out what the coefficients are. So 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, and 1. Now all I need to do is simply compute. So I'll evaluate the powers to begin with. X to the 5, and then anything to the power of 0 is 1. Next, 5, x to the 4, and then minus 3 to the power of 1 is minus 3. 10x cubed, and then minus 3 to the 2 is minus 3 times minus 3, and that's 9. Becomes positive because double negative. X squared, then minus 3 times minus 3 times minus 3. Well, 3 times 3 times 3 is 27, but because it's negative, or there's 3 negatives, it's going to become minus 27. Next, 5x to the 1, don't need the 1. Minus 3 to the power of 4. Because it's an even power, the negative's going to get cancelled out. So that means 27 times 3 is 81. So it's positive 81. And then finally, x to the 0 is simply 1. So I can leave that out. So it's going to become minus 3 to the power of 5. And that will be 243. Okay, now let's deal with these brackets. So that will be, first one will be x to the 5, so I just ignore the 1, plus, we've got a negative here, so it's minus 15x to the 4, plus 10 nines are 90, x cubed, minus 270 x squared, plus 581s are going to be 405, and that will be x, and then minus 243, thus demonstrating how we can expand something to the power of 5 using 1, 2, 3 simple step. Alright, final one and trickiest one of them all. We want to expand. Now we've got to the power of 5 and we're dealing with non-1 coefficients here. So you got a 3x and you got a 4 and it's minus just to make it trickier. Alright, what we're going to do is we're going to employ the exact same pattern we used before. So it's to the power of 5. Now running this out, I simply go, my a is going to be 3x in this instance, so it's 3x to the 5 multiplied by minus 4 to the 0 plus 3x to the 4 minus 4 to the 1 plus 3x to the 3 minus 4 to the squared plus 3x to the 2 minus 4 to the 3 plus 3x to the 1 minus 4 to the 4, and then final we have plus 3x to the 0 and minus 4 to the 5. Now I remember from before, the coefficients for the fifth order are 1, 5, 10, 10, 5, 1. Now all I need to do is deal with the powers and then do the multiplication. So the 1 can be ignored from over here. So this will become 3 to the 5, x to the 5, and then negative 4 to the 0 is just 1. Anything to the power of 0 is 1. Next, 5, 3 to the 4, x to the 4, and then minus 4, plus 10, 3 cubed, x cubed, and then minus 4 squared, that is going to be 16. Okay, plus we've got 10, 3 squared, x squared, and then 4 cubed is going to be minus 64, because it's negative. Okay, plus 5, 3 to the 1, x to the 1, don't need to show that, and minus 4 or negative 4 to the power of 4 is going to be 256. Plus, we've got the 3 to 0, which is 1, x to the 0, which is also 1. So that's just going to be minus 4 to the power of 5. And minus 4 to the power of 5 is going to be, well, firstly it's going to be negative, and then it's 4 times 256, so that's 1024. Alright, cleaning this up, 3 to the 5 is going to be 243, x to the 5. Next we've got 5. 3 to the 4 is 81, x to the 4. And then we've got the minus 4 here. Plus, we've got 10. 3 squared is 27, x cubed, multiplied by the 16, plus 10. 3 squared is 9, x squared, multiplied by a minus 64, plus 5. Well, we can evaluate this one. We can go 15x times 256, and then minus 1024, and I can keep going down. Okay, continuing the evaluation, we've got 243 x to the 5 minus 2081 x to the 4 plus 270 x to the 3 plus 640 9x squared plus 15 times 256, that's going to be 3840x, and then minus 1024. Okay, finishing this off, 243x to the 5, then 20 times 81, that's going to be 1620x to the 4, plus 270 times 16 is 4320 x cubed, minus 640 times 9 is 5760 x squared, plus 3840 x minus 1024, thus arriving at the final expansion. So in summary, for this lesson, what we set out to learn was how we can expand higher order brackets. The way in which we do this is we use Pascal's triangle to predict the coefficients, and then we just employ the binomial expansion pattern. So we go up powers, down powers, and then stick the coefficients in front. Once we've got the pattern as shown over here, we just evaluate what we have in front of us, thus arriving at the final expanded form.